This is Chapter 8, Section 2. We are going to talk a little bit about Section 3 out of this book too, but the focus of Section 2 is all about the 5 types of chemical reactions, and you'll need to make sure you get all of these down along with the examples. Make sure you understand about the reactants and products and be able to predict products of these reactions. That will be very important too, predicting products. So the very first type of reaction we have, and I would label these, again, you're going to have 5. The first one is combustion. This is where you have the burning of any substance in oxygen that will produce heat. So A and B, the letters A, B, C, and D are going to be very generic when we use those here. So A is going to be any substance burned in oxygen. So oxygen is a reactant to produce a product, and it can be one or more products that are produced. A very common type of combustion reaction involves what we call the generic classification of hydrocarbons. So if I look at this compound that is given here, CH4, which is really methane, it is called a hydrocarbon because the compound itself contains hydrogen and carbon. You will see several more examples either within this podcast or during class where we look at different combustion reactions and we go through those. Also, too, if it's a hydrocarbon plus oxygen, the products will always be carbon dioxide and water. And this is already a balanced reaction again. So a hydrocarbon plus oxygen will always produce carbon dioxide and water. So your products will contain oxygen, and again, if it's a hydrocarbon reacting with oxygen, it will form carbon dioxide and water. Here's another example of a combustion reaction, which is sodium plus oxygen. And this one right here, because it is a group 1 metal, if you remember we talked about group 1 metals earlier, and group 1 metals are very reactive. In this case, I can tell you when the group 1 metal or a group 2 metal reacts with oxygen, heat is given off. And that was part of the definition for combustion reaction, is heat is given off during this process. So oxygen is a reactant here. And in this case, when you put sodium and oxygen together, you get sodium oxide. And sodium oxide is an ionic compound. We would cross over charges to get the Na2O. And sodium oxide energy or heat would be given off during this reaction. If you were to take something like iron and try to react iron with oxygen gas, yes, that's a metal. But what you're going to get is some type of iron oxide, or think about it as being rust. That does not give off a lot of heat during the reaction. So this would not be considered a combustion reaction, would not be considered one. It is a reaction we'll get to, because even though oxygen's a reactant, it does not give off heat during the reaction. So again, there is that first reaction. It is now balanced. And the second reaction, C3H8. C3H8, this is propane gas. And propane gas reacting with oxygen, that is another hydrocarbon. So if I gave you this reaction and said predict the products, you should be able to predict that carbon dioxide and water will be produced. Carbon dioxide and water will be produced, and then you would have to go back and balance this reaction. You will get plenty of practice balancing reactions, especially combustion reactions, and I'll also teach you a little trick with the combustion reactions as we go through some of these. There is this one, balanced. That's the first type of chemical reaction. The second type of chemical reaction is called a synthesis reaction. This is where you combine 2 or more substances to form a compound, and you only have one product. So the key to synthesis reactions is one product. So one compound will be produced from 2 or more reactants. 2 or more reactants. In this example right here, we have hydrogen and chlorine gas producing hydrochloric acid, or HCl. As a reminder, your diatomic elements. So hydrogen and chlorine are both diatomic elements. They are in their diatomic state. Whenever they combine to give you HCl, you see it here. It is produced. As I look at the animation or the picture that we have right here, chlorine gas is this yellow-brown colored gas that you see in the flask. Hydrogen is in the lectern bottle right here. So the hydrogen gas is coming out of the hose. It is coming down through here. And right there, wherever it hits the chlorine gas, you see almost a flame there. So it is an exothermic reaction to produce the hydrochloric acid or gas. So if you were having to predict the products of a synthesis reaction, the easiest one is going to be ionic compounds. So you're just looking at charges and crossing over charges of your more than likely two different reactants to produce your one product. But if it's a covalent one, it can be harder to tell. The previous reaction we just looked at was covalent. Hydrogen and chlorine are both nonmetals. But since it was just two elements, great, we're going to come up with what that needs to be. But it could be a lot harder to tell. That first one, though, ionic, that's the one that you should be very comfortable with predicting products. So in this example right here, aluminum's a metal, chlorine is a nonmetal. If I were to look at their charges to predict products right here, aluminum is a 3+, chlorine is a 1- charge, and when I cross over charges, I'm trying to change my colors here, the 3, the understood 1, you will get AlCl3. Again, just something else I want to point out, aluminum, notice it doesn't say Al2 because aluminum is not a diatomic element, yet chlorine is a diatomic element. That's why you see a 2 on it. Once you predict your product here, you would go back and balance that chemical reaction to get the proper coefficients. And there is this reaction that has been balanced. So that is reaction type number 2. Heading on over to reaction type number 3, it is decomposition. So with decomposition, the key to this one is there is only one reactant. And that one reactant, which is generic here, AB, will break down into 2 or more products. So one reactant breaks down into 2 or more products. In this example, it shows water decomposing. This process where water, you can't see it because it's not in the picture, but these 2 leads right here are hooked up to provide electricity. So this process is called electrolysis. So water, think of it as being electrocuted, and it's breaking it down into the 2 elements that break up water, which is hydrogen and oxygen. Again, if it breaks it into hydrogen and oxygen, hydrogen is diatomic, oxygen is diatomic, and since they are by themselves there, they are in their diatomic state. And then they have balanced this equation. So water is going through electrolysis here. There was water fully within both of these tubes, but as the water breaks down and gas collects, you can see that the gas is being collected right there at the top of each tube. Hydrogen is going to be in this tube over here to the left and oxygen in the tube to the right. So again, if you were having to predict products, if you have a binary compound that's your reactant, binary meaning just 2 elements, then you will break that compound into the 2 elements that make it up, like the example we just saw. But if you have a product, or a reactant that is 3 or more elements, then it can be a lot harder to tell. I do want to go over a couple of examples, though, after we get through with this first one. So KBr, potassium bromide. It's saying it's in its liquid phase. Since there are only 2 elements, then you will break it apart into potassium and bromine. Potassium is not a diatomic element. You leave it as K. It is in the solid state because that is a metal. And then bromine is a diatomic element, so when it breaks apart on its own, it has to be in its diatomic state. And bromine at room temperature is in the liquid phase. And then you would go back and you would balance this one and get 2, 2, 1 as your coefficients. So right here I'm going to go over a few other types of decomposition reactants or decomposition reactions where your reactant does have more than 2 elements. So the first one, if you have a metal carbonate, and I'm going to pick calcium. So calcium carbonate, that is the formula for it. Calcium has a 2+ charge, carbonate has a 2- charge, so those charges cancel. It is an ionic compound. Calcium carbonate, whenever it breaks down in a decomposition reaction, add a little bit of heat to it, it gives off calcium oxide and carbon dioxide gas. Now, since it's a metal carbonate, it breaks down into the metal oxide, so M for metal oxide, and carbon dioxide gas. So I could pick any other metal. Let's say I picked magnesium carbonate. Well, magnesium carbonate would break down into magnesium oxide and carbon dioxide gas. Or potassium carbonate, that would be K2CO3, but potassium carbonate would break down into potassium oxide and carbon dioxide gas. So I'm going to use a capital M here for our metals. Another one, what if you had a metal hydroxide? I'm going to pick calcium again. Calcium, again, has a 2+ charge, but hydroxide has a 1- charge. So when you cross over charges, it would be CaOH2 in parentheses. Again, you would have to cross over charges there. This time, what is produced, and I'll write it before I actually write what it is, a metal hydroxide will break down into a metal oxide and water. A metal oxide and water. So in this one, that would be calcium oxide. Well, calcium's a 2+, oxide's a 2-. So calcium oxide and water. And this would, you would go back and balance all of these two as needed. So far, these first two, they are already balanced. The next one that we will look at is the decomposition of metal chlorates, and chlorate is ClO3. So metal chlorates. Sticking with, let's go to potassium this time. Potassium's a 1+ charge. Chlorate is a 1- charge. So that's charges cancel. It's KClO3. And in this one right here, it would be heated. We would also have another compound added to it, a type of catalyst. And this time, what is produced with the metal chlorates, you would have your metal chloride and oxygen gas. Metal chloride and oxygen gas. So potassium is my metal. Chloride is a 1- charge, so that is KCl. 1+, 1-, which cancels. And oxygen gas. And in this one right here, you would go back and balance it, and your coefficients would be 2, 2, and 3. For this last one we just did, if I picked a different metal, let's say calcium chlorate. Calcium chlorate, that would be CaClO3 2 because of your charges. That would produce calcium chloride, again, crossing over charges, and oxygen gas, and you would go back and balance that equation. And we're going to do one more type. How about the decomposition of acids? So for our acids, if you are decomposing those, here's one example. H2OCO3 is carbonic acid. That would be in its aqueous phase. Carbonic acid would break down into a substance and water. So water is going to be produced and one other substance. Let me give you another example, H2SO4. would break down and water would also be produced with it. Let's just kind of look back to make it easy. H2O, if I were to take off the two H's in the O, so lose my two H's, lose one of my oxygens, I would be left with CO2. I would be left with CO2. If I do that same line of thinking with H2SO4, again, just trying to make it easy here, take off two hydrogens and one of the oxygens. Again, two hydrogens, one of the oxygens leave here. I am left with SO3. So there's you a couple of examples of decomposition of acids as well, and both of those are already balanced. Please make sure you get all of these extra examples of decomposition where you have more than two elements that make up your reactant. Here is our fourth type of reaction. It's called single replacement or single displacement. Either one is fine. You'll see me abbreviate it SR. Single displacement is good as well. It just depends on which textbook you're looking at. And this is where you have one element that replaces another. So the way I like to look at it is this is considered my free element, and it wants to replace something within compound BC. Well, in this example, I noticed that A is paired up with C in this particular one. So A must replace B, kick B out all by itself, and then A and C get together in this one. The way it works is your free element, typically if your free element is a metal, then it replaces the metal in the compound. They have the examples up here talking about metals replacing metals, nonmetals replacing nonmetals, but they do put the plus and the minus. So if your free element is a metal, you know metals typically have positive charges. It will replace the positive charge in whatever compound BC is. And positives always come first. Negatives are going to come last. So cations first, anions last within a compound. It is possible, though, occasionally hydrogen, that'll be the only nonmetal we talk about, might be at the positive charge within compound BC, and you could have a metal replacing hydrogen too. If we were to turn it around and you had A plus BC and it produced C plus AB, then in that example it means A is kicking out C. C's coming over here and A and B are getting together. That means A and C were probably both nonmetals. A and C were most likely both nonmetals and would typically carry a negative charge if they were standalone. So this is just showing you the arrows like what I had shown you there, and getting into just a little bit more about single replacement. In this reaction right here, we've got copper plus silver nitrate. Again, you have your free element copper. It's a metal, and within silver nitrate, silver is a metal. So copper wants to replace silver, kick silver out, and now copper and the nitrate ions can get together. That is an ionic compound, so you would cross over charges to get your proper formula there. Now, with your products, you will produce, if you're starting off with a free element and a compound, then you will produce a free element and a compound. And for this right here, it doesn't matter which order you write your free element and compound in. They could be flipped, compound plus free element. But that's typically the way this works right here. I want to look at this last little part. It says your free element must be more active than what it wants to replace. So if your free element is coming in here to kick something out of your compound, it must be more active. I'm going to go show you the activity series real quick, but that periodic table packet I gave you, on the back of the periodic table is a copy of this activity series. Now, in class, just know, even though I am briefly going over this right now, when we start to get to examples and even our tests when we have it over Chapter 8, we will not be using the activity series. I'm going to test you mainly over identifying the 5 types of reactions and then balancing them. But just so that you have seen the activity series, know kind of how it works. On the left side, you have your activity of metals, and as you move up, it says you have increased activity. So notice your group 1, group 2 metals are here at the top. They're going to be more active than some of your group 2, group 13 D block metals. Notice when you get to the block down here at the bottom, silver, platinum, gold, you're talking about heavy metals, copper, mercury there at the bottom, and hydrogen is right there. It's the only non-metal you're going to see within the activity of metals. And over here on the right-hand side, you've got your activity series for your halogens. That's group 17. Notice they are in order that they are within group 17. Fluorine on top is the most active of our halogens. So in this example right here, we have iron plus copper sulfate. If you did go back and look at your activity series, iron as our free element is more active. Since it's a metal, it wants to replace the metal in the copper 2 sulfate. So it will kick the copper out. There's our copper, and iron and sulfate get together. Well, iron, it could be hard. I mean, it's either a 2+ or a 3+ charge. We will just go ahead for now and assume iron is a 2+ charge. Sulfate is a 2- charge. Since those charges cancel, you get FeSO4. And this reaction is complete just the way it is. I do want to give you one other example, just so that you can kind of think about these things. Let's say that you had fluorine plus NaCl. So fluorine is our free element here. Well, fluorine is a non-metal, so it wants to replace our non-metal, or whatever's normally a negative charge. That's the chlorine. So fluorine will come over. It will kick out chlorine. Chlorine will come over. That is Cl2. Chlorine is by itself, so it has to be in its diatomic state. And then the Na and the F get together. Well, sodium has a 1+ charge. F has a 1- charge. That is NaF. And then you would go back and balance this. That would leave a 2 in front of the NaCl, a 2 in front of the NaF. That is a balanced reaction. And just real quickly, this last example that they're given here, bromine would want to replace chlorine because, again, it's a non-metal. But if you look back at the activity series, bromine is not more active than chlorine. So this reaction will not take place. That stands for no reaction. And our last type of reaction, the 5th one, is called double replacement or double displacement. You'll hear me call it for us double replacement, or DR. We're going to stick with the very basic double replacement reactions, meaning you have 2 compounds that swap partners to create 2 other compounds, and all 4 compounds we're going to stick with ionic compounds. So 2 ionic compounds create 2 ionic compounds. If they're going to be ionic, remember cations are always first and anions are always last. So your cations are going to swap partners. So A and C are going to swap partners. That's what you have over here. Or B and D swap partners. It doesn't matter which way you look at it, you will get the same 2 products. And again, those 2 products at the end can be written in either order, but cations first, anions second. In this example, again, we have 2 ionic compounds. Lead and potassium are our 2 metals, so think of them as swapping partners. Since you are predicting the products, then you have to look at charges. So lead over here had a +2 charge. It still has a +2 charge there. Potassium always has a +1 charge. Nitrate, right in there, has a -1 charge. Those cancel. Chromate on your table of ions has a -2 charge. Those charges cancel, and that's why you see the products that you do, because if you're predicting products, you will have to work with charges for these ionic compounds. Oh, also too, in this example, since we're going to be doing reaction types in our lab at the end of this chapter, notice in this example you have a clear colorless liquid and a clear yellow liquid. But when you put them together, this yellow that is being produced is a yellow solid, And I told you earlier, when you put two liquids together in a solid form, that's called a precipitate. This right here in solid form, that is the precipitate that is being produced. Precipitate is being produced. So again, with our products right here, you can switch your positive ions or switch your negative ions. Just remember, cations first, anions second. And then we look at something called a solubility table. So again, in that periodic table packet, on the back side of your periodic table, I also have a picture of the solubility table that we could refer to. Again, I just want you to be familiar with it, but I will not be technically testing you at this level over solubility rules, but I do want you to know that they exist. So here are those solubility rules you'll find in your packet. Solubility rules is just saying basically what will actually dissolve in water. If it will dissolve in water, then it's considered soluble. If it will not dissolve in water, it is considered insoluble. And here are the most basic of those solubility guidelines. Again, I will show you a reaction that is based off of this that will not react. But everything we're going to work with, we're going to assume these double replacement reactions will take place. In this first example, you have your lead 2 nitrate and potassium iodide. These will actually react with each other. So my lead being a metal will cross over paths with the potassium. And if you had to predict the products, your lead with a 2+ charge is going to be with iodine and a 1-. That is PbI2. And your potassium with a 1+ charge and your nitrate with a 1- charge. Those charges cancel. So you are left with KNO3. I know with the solubility tables, lead is a heavy metal, very common for it to be insoluble. This will be my precipitate. The other is left as aqueous solution. And there it is balanced. And then the last one, again, if you had to predict products here, your Na, your sodium, and your potassium are both metals. They would swap partners. So notice everything here. Sodium's a +1, nitrate's a -1. Potassium's a +1, iodide is a -1. So even when you cross over charges, you're still going to get everything has charges that cancel. So sodium is now paired up with the iodide, and potassium is with the nitrate. But if you were to look at your solubility rules, both of these are considered soluble. So they will dissolve in water, so you will not actually get a precipitate or a solid that is formed in this reaction, and in that case, that would be a no reaction. You will get lots of practice with these 5 types of reactions and balancing them.